And then in week 5, we moved on to some more kind of detailed theory about the statistical testing that we were about to go into. And we talked in a bit more detail about this idea of the sample versus the population distinction. And that's what this image is demonstrating, this idea of the sample being representative of the population and repeated sampling of samples being representative, once we aggregate them together, of what's really happening at the population level. So the example on the left-hand side here is demonstrating sampling variability, this idea of different samples being slightly different even if they're all representative of the population. So to use an example here, let's say that what we're measuring is looking at the number of coffees that people drink in a day. So the population average is three coffees a day. And any individual sample that we take, made up of 4 people, is going to have a slightly different average when we look at the sample average. So some samples might have an average of 3, some samples might have an average of 2, some might have an average of 5, some very sad samples might have an average of only 1 coffee a day. That's sampling variability. That's the idea that even if a sample is representative, there's always going to be slight differences between the samples. But then once you take all the samples together, you're then going to be able to approximate what's actually happening at the population level. And it's the same kind of principle that we engage in when we're conducting research, that what we're doing is looking at a sample, so the sample that we've got from our individual research project, and we're wanting to use information in that sample to make a generalization back to a population. And the more samples we have, the more, and when we can aggregate or kind of average across them, the more representative of the population it's going to be. But also the bigger the samples are, the more representative any individual sample is going to be of the population, because the less sampling variability there's possibly going to be. So that was the idea that we talked about back in week 5. And then extending on that, we moved on to talking about the normal distribution and using very fancy mathematical theory, statistical theory, that tells us that if we have a certain kind of test statistic, we can actually know how likely it is that that particular value could occur if the null hypothesis is true. So if the null hypothesis that there's no effect in our population is true, we know from fancy mathematical theory, statistical theory, about how likely it is that we've obtained any particular effect, any particular test statistic in our sample, if the null hypothesis is true. And so that information that we have then gives us the probability, the likelihood or the chance of obtaining any particular test statistic, any particular value under that null hypothesis. And that directly feeds the actual numbers that we get from the test, the statistical test that we run, specifically the p-values that we get, which we use to either reject or to not reject the null hypothesis. And the p-value specifically, that actual number, is giving you the probability or the likelihood or the chance that we have got this particular pattern of results, we've got this particular test statistic, if the null hypothesis is true. And what that means is that the smaller the p-value, the less likely it is we've got this particular test statistic if the null hypothesis is true. And therefore, the more likely it is that we've got this particular test statistic because the null hypothesis isn't true, but in fact because there actually is a real effect in the population. So the bigger your test statistic, the bigger the number, the smaller the p-value. So the bigger your test statistic, the bigger the value of t or the correlation or the chi-square, the smaller your p-value becomes. And a small p-value is saying that the null hypothesis is very unlikely to be true. The probability of it being true is very low. And therefore it's more likely that the alternate hypothesis, H1 rather than H0, is true. And therefore we can use that as evidence to support the alternate hypothesis. So that's the principle that we follow when we're running these individual statistical tests. But it is quite an indirect principle. It's one with a lot of steps involved, which is why this is a very imperfect process that we follow. In terms of actually engaging in this hypothesis testing process that we do, There's two different ways that we've talked about and we've actually practiced ourselves to run this hypothesis testing process to get our actual statistical tests and to get the answer of whether we've supported or not supported our hypotheses. And the one on the left-hand side is when we calculate our test statistics by hand. And we did this for most of the tests that we ran, not all of them, but most of them, in order to actually calculate manually our test statistics, so our t statistic or our chi-square statistic. And we used that information, then compared that with critical test statistic, being critical t or a critical chi-square, and then to see whether that supports, whether we then reject the null hypothesis or not reject the null hypothesis. But the more common way of doing the same thing is by using a computer program, for example, Stata, to do this calculation for us. So not to do it by hand, but to put the data into a stats program and to get the stats program to calculate the test statistic for us and to give us a precise p-value. And that's the much more common way because we have the power of the magical power of computers and computer programs. And that's why we focused more of our time on doing it that way rather than doing it the by hand way, because I think it's more important that you can learn that and learn to interpret the output from the programs themselves.